We will talk a little bit more about the proof system. We will mention the completeness theorem, but we will not prove it. And then we will move on to discuss connection to algorithms and connection, and then Gödel's incompleteness theorem. So that's a lot for 3 lectures. I remind you that we have the tutorial on Monday morning, and we have the special meetings on Wednesday at 5. So next week we meet every day except Friday. Okay, so we had our set of axioms, and what do we know already about our... so we talked about it's the syntax, and we talk about the formal proof system, and what do we know about the formal proof system so far? The one thing that we proved is so Theorem 1 was the soundness. And soundness was the connection we said between syntax and semantic. And it said that if gamma can prove alpha, then gamma logically implies alpha. And this can always be used to show that certain things are not provable. So if I want to show that something is not provable, so say I want to show, so here is an example of the use of the soundness theorem. Say I want to show that say there exists an x such that p of x, there exists an x. So from there exists an x such that p of x, say I want to show that I cannot prove that p of x. Right? We showed last time that from p of x I can prove there exists an x such that p of x. Now I want to show you that I cannot prove the inverse direction. So how do we show it? So how do we prove such a statement that this cannot be proven? So the trick is to use the soundness, which makes it much easier. Because, so here is the proof of this claim. So assume by way of contradiction that there exists an x, p of x, can prove p of x. Now I can invoke soundness. So by the soundness theorem, we get that there exists an x, p of x logically implies p of x. So what does that statement say? That statement says that in every structure and for every assignment S that satisfies this, the structure and the assignment must satisfy this. Now it is easy to we get a contradiction by constructing a counterexample. So get a contradiction now by construct a structure M and an assignment S that will violate this. So what does it mean it will violate this? Such that M under the assignment S does satisfy there exists an x such that p of x, and at the same time M under the same assignment S does not satisfy p of x. That will violate this claim, and therefore we will violate this assumption by contradiction. So can you give me an example of such a structure and such an assignment? So we need to come up with some simple structure, some simple interpretation of the relation symbol P that will allow us to show this. That should not be difficult. Yes?
So let's say if we take M as the universe of M is a natural number,
Okay.
and P is a relation symbol of greater than 5.
Okay, whatever. Right. So we'll let M be. We need a structure for this language, for the language with P. So we need a universe. So the universe can be the natural numbers. And we need an interpretation of P. P is a one-place relation. The interpretation of P is just a subset. Which elements of my universe satisfy P? So say P is the set of all n such that n is even. Right? So an interpretation of a one-place relation symbol is a subset of elements. Interpretation of two-place relation symbol is a subset of pairs, like x is less than y and so on. So P is satisfied, which means that M under an assignment S satisfies P of x if and only if S of x is even. Because S maps variables to elements of my universe. So S of x is a natural number. So this interpretation is exactly what it means is the second line. Okay, so now I claim that M satisfies under this assignment. So I have to define an assignment S. So I want to define an assignment under which this is going to fail. So we pick S such that S of x equals 1. So clearly, M under this assignment S does not satisfy P of x. Because we said that it satisfies P of x under some assignment S, even only if it assigns to x an even number. But on the other hand, M under this assignment S does satisfy the existent x such that P of x, because this is satisfied if and only if this is equivalent to saying that there exists some element n in my universe such that if I take M and in S I assign to x this element n, I will get P of x. You remember, so the semantics of there exist, or for all was that for every element that I'll take for x, it will be satisfied. And there exists an element in my universe such that if I assign x to it, it will be satisfied. And such an n exists. For example, pick n to be 2. So to show the soundness theorem can easily help us show that things are not provable, because it just translates into showing that they are not logical truths. Yes?
I was wondering, do we need to change your definition of S in order to satisfy the...
No. So S does not change. We say that, just have to recall the definition of the semantics. M under an assumption S satisfies for all x alpha if for all A in the universe of M, if I take M and now I keep the assignment S as it is, but I just replace whatever S gave to X by A. This will satisfy alpha. That's our definition of, this was our definition of semantics. This is the way we defined the semantics of this. And similarly, M satisfies under an assignment S. So I don't change S. It's just a question of how to interpret the quantifiers. And the quantifiers mean S could be maybe in alpha there are other variables, Y, Z, and I keep the assignment of S for those. But it's true for all X. If I don't care what I'll assign for X, I can keep S as it is, but change things for X, such that that will be true. So it all boils down to the definition of semantics. So this was the definition of for all, and this was the definition of satisfaction of there exists. But this is something that you should feel more comfortable with, like the definition of semantics, how to show that the structure satisfies a formula, doesn't satisfy a formula, and so on. Okay, so this was the soundness theorem. Now let me mention some more theorems about some more properties of our proof system. So the next property is the deduction theorem. I think I mentioned it last time as well. So theorem 2 is the deduction. Theorem, and it says that gamma can prove alpha eros beta if and only if I take gamma and add alpha to it, I can prove beta. And we said that the proof was exactly like the proof in propositional logic, because all the proof involved was the semantics of, the tautologies that are related to arrow and the tautologies that are related to modus ponens. So it's the same proof, the same result. And then our third theorem that we also mentioned last time was that the two definitions of consistency are equivalent. So there exist the following two statements are equivalent, and statement 1 was, so this was our third theorem. Statement 1 was that there is some alpha such that gamma cannot prove alpha. And the second statement was that for no alpha can both gamma proves alpha and gamma proves not alpha hold. And if any of those two properties are satisfied for gamma, we call it gamma is consistent. And again, this is a property that we saw in propositional logic, and the proof is the same proof that we saw in propositional logic. So in that respect, we are the theorem 2 and 3 are the same as in propositional logic. Now I want to mention a theorem that is special to first order logic. So this is called the generalization theorem. The generalization theorem. And the generalization theorem states that if gamma proves alpha and x is not free in any formula in gamma, then gamma can prove for all x alpha. So at first sight, it looks a bit surprising. How come if I can prove alpha, I can prove for all x alpha? But the point is that the assumptions don't mention x at all. If the assumption don't mention x, and I can prove something about x, I mean, there are two options here. X appears in alpha and x does not appear in alpha. If x is not free in alpha, then for all x alpha and alpha, they mean the same thing. And we have an axiom that says alpha arrows for all x alpha if x is not free in alpha. So if x is not free in alpha, there is no meaning to this. This is interesting if x is free in alpha. So alpha tells you something about x. But alpha tells you something about x that I can prove it without mentioning x and the assumptions. If I can prove it without mentioning x and the assumptions, then it will hold for every x. That's the intuition behind this claim. The other thing to note is, so maybe two things to note. First of all, note that the reverse is always true. Why is the reverse always true? Note that it is always the case for every gamma that if gamma can prove alpha for all x alpha, then gamma can prove alpha. Why is this true? Just as axiom 2. Because axiom 2, we have axiom 2 that tells us that for all x alpha arrows alpha tx, which is substitute the term t for x, and alpha is just alpha with x substituted for x, and substituting x for x is always a legal substitution. So therefore I get, in particular, for every alpha, for all x alpha arrows alpha is a case of axiom 2. So if I have for all x alpha arrows alpha, and gamma could prove for all x alpha, how will I prove alpha? I want to prove alpha. I know that gamma can prove for all x alpha. And this is an axiom. So how will I prove alpha? Yes?
You just take an instance that approves before.
What?
You take one of them that approves, that approves for all x, you just take an x that approves and put that into.
Gamma can prove for all x alpha, and I know that for all x alpha arrows alpha is an axiom. Now I want to show that gamma can prove alpha. I just do mod exponents. I just write, I start with gamma, I have here a proof that proves for all x alpha, because I assume that gamma can prove for all x alpha. Then I use for all x alpha arrows alpha, which is axiom 2. And then I use modus ponens, and I got a proof of alpha, because this cuts. So if I had a proof of for all x alpha, then I can extend it to a proof of alpha. So whenever gamma proves for all x alpha, gamma proves alpha. But what we want here is the opposite direction. We want to start with the assuming gamma can prove alpha and prove that gamma can prove for all x alpha. It's a bit confusing, but it's not very difficult. Now, we do have an axiom that tells us alpha arrows for all x alpha. But why can't I use this axiom here? What was axiom 4? If you look at your notes from last time, what was axiom 4? What?
Alpha arrows for all x alpha.
Right. Axiom 4 was alpha arrows for all x alpha
When
x not free in alpha. Now, the problem is that we want to prove this theorem. Here we didn't assume that x is not free in alpha. We only assume that x is not free in the assumptions. This is kind of the uninteresting case. X is not free in alpha. It doesn't cost you anything to say for all x. It comes for free. But here I don't assume that alpha can talk about x. It's just an assumption that it doesn't show. So this is not relevant. Therefore, cannot be applied to prove the generalization theorem. Okay, so we had two comments. One of them that the opposite direction is easy to prove, and the other that we don't have such an easy proof for the generalization theorem itself. We need to do something different. Okay, so how are we going to do it? Where is all the experts on how are we going to prove? I mean, it's a good intuition, but formally it's not a proof. Because I want to show you that we have a very clear definition of what is a proof from gamma of this. I don't have any, it doesn't allow me to change gamma. The definition says gamma can prove this if I can have a sequence of formulas, each of them is either an axiom, either a member of gamma itself, or obtained by modus ponens. Yeah, I was waiting for you to give me your generic answer.
Generalized induction?
Right,
it's
of course.
called the generalization theorem.
Okay, but it's a different generalized, right? So why is it kind of a good candidate for using induction? Because I can rephrase the generalization theorem. I can rephrasing it, the generalization theorem can be rephrased as if alpha belongs to I of gamma union axioms using modus ponens, then for all x alpha belongs to the same set, gamma union axioms, modus ponens. Right? Because to say that I can prove alpha just means that alpha belongs to this set. So it's a claim about every element of this set. So if I have a claim about every element of such a set, the claim is for every alpha in this set, for all x alpha is also in the set. Yes?
Don't you need to clarify that with if, provided gamma.
Yeah, providing.
X is not free.
Yeah. Of course. But I'm just saying here, provided x not free in gamma. But the point is that if we restate it like this, we can see that this is a statement about every element of a set which is inductively defined. So whenever I have a statement of the form every element of an inductively defined set, my first approach should be to try generalized induction. Okay? So there's even deeper reason than just the name. Okay, so if we want to do generalized induction, so we do the proof by generalized induction. So what is my base case? What is the induction, the basis of the induction? What could be alpha? Either an axiom or it is in gamma. So if alpha is in gamma, case 1, gamma, alpha is a member of gamma. Now this is an easy case, because if it's a member of gamma, then we know that then x is not free in alpha. So we can invoke axiom 4, alpha arrows for all x alpha, use alpha as an assumption, alpha is an assumption, and then use modus ponens and get for all x alpha. Because if alpha is a member of gamma, our assumption was that all members of gamma don't have x. So this is kind of following the intuition of what you suggested, right? This is the base case, case 1 of our base case. If alpha was in gamma, I can in some sense take care of all x alpha. So what will be case 2 of the basis of the induction? What else? What other options for alpha there is in the basis of the induction? Yes?
Alpha is one of the axioms.
Right, alpha is one of the axioms. Now how shall we handle this? So case 2 is alpha is an axiom. So how should we handle this? How do I show that I can prove for all x alpha? Yes?
We put class all axioms are logical truth.
So you're going to the semantics, and I'm talking about pure formal proofs. It's completely syntactical.
Do we have the completeness theorem? So if it's a logical truth, we can complete it.
We don't have the completeness theorem here. We are just trying to understand our formal proof system. Yes?
Axioms are closed under the for all.
Right. You have to just refer to the definition of our axioms. The axioms were closed under adding for all x. You remember the axioms were those 4 types, and then we said we close it. We said that axioms, the set of axioms was I of A1 up to A4, and then we close it by adding all the for alls. If alpha is an axiom, for all x alpha is also an axiom. That was our definition of the set of axioms. So the set of axioms is closed under adding for all quantifiers. So if alpha is an axiom, for all x alpha is also an axiom. Okay, so now we are in the induction step. The induction step. And what is the induction step? So alpha was obtained by modus ponens. So we had alpha, we had the, so induction hypothesis. Can anybody tell me what will be the induction hypothesis here? And what do we have to prove? And I want to say, what do we need to prove? So our operation is modus ponens, which means the induction step, you have to assume that alpha was obtained by applying modus ponens. So what will be the induction hypothesis, and what will be the step that we need to prove? It's not a good sign. We are. You'll have to do a lot of those in the final exam. Yes, what do you suggest?
Okay, our assumption is that beta implies alpha is provable, beta is provable, and now we're trying to prove that for all x, alpha is provable.
We have to be more careful about it. I was not getting too excited.
Our assumption is that beta implies alpha is provable, and for all x, beta implies alpha is provable. No?
Anybody? The trick is whenever you have to, that's the difficult part on proof by induction. We have to be careful about stating the induction step. The induction step is we take what we want to prove. We want to prove that if alpha is provable, then so is for all x alpha. Now we replace the alpha by the input of our function. So do you want to give it a try?
I was going to say, so if beta is provable, then for all x, beta is provable. And if beta implies alpha is provable, then for all x, beta implies alpha is provable.
That's almost there. Because we don't need the if. Alpha was obtained by alpha equals beta. So you see, we go along, you can think of it like this. We go along a sequence of a proof. So we have a proof. The proof is, say, phi 1, phi 2, phi k. And we want to show that at the end, this is a proof of alpha. This is a proof of alpha. Now we want to show that we can add, we can replace this guy by for all x phi 1. We can replace this guy by for all x phi 2. And at the end, that we'll be able to replace this guy by for all x alpha. So we are going along this sequence. And we want to show that at each step, I can replace the phi by for all x phi. So if I finish the proof, I have shown that I can replace alpha by for all x alpha. So we started here. We said, if phi was an assumption from gamma, what could have started the sequence? Phi was an assumption for gamma. We showed that we could replace it by for all x phi. Phi could be an axiom. We showed that we could replace it by for all x phi. Right? So now we took care of those two cases. So I get to this phi k. How could it have been generated if it was not an axiom, it was not a member of gamma? By modus ponens. So what does it mean? It means that here before phi k, so say I have here some gamma. So instead of calling it gamma, phi k, call it gamma. I arrive to this gamma, and I say I already proved everything for all the way here, that I can add the for all x. How was this gamma generated? I had here at some point beta equals gamma, and at some other point I had beta. And gamma was obtained by applying modus ponens. What is the induction hypothesis? The induction hypothesis says that up to here, I've already proved everything I need to prove. So I already proved that I can prove for all x beta equals gamma. So the induction hypothesis is that gamma can already prove for all x beta equals gamma, and gamma can prove for all x beta, and I need to prove that gamma can prove for all x gamma. So the induction step is I got to a gamma here, and I'm in this step. Everything here I could take care of. I could show my theorem for everything up to this step. And gamma was obtained by applying modus ponens. So I know that at some earlier stages, I had some beta errors, gamma and beta. The induction hypothesis is that I could already do what I need to do for everything that appeared earlier. So I could prove for all x beta errors, gamma, and I could prove for all x beta. And now I need to show that I can push this result further to swallow gamma as well, to cover gamma as well. So the induction hypothesis is that I could prove for all x beta equals gamma, and I could prove for all x beta. And now I need to show that I can prove for all x gamma. I want to extend this addition of for all x to gamma as well. That's a very crucial point to understand in this course. I think I should almost now kind of vow that in the final exam you are going to have definitely at least one induction, but maybe more than one. That this is crucial. To understand how do we do proofs by induction, by generalized induction, we have a statement, and we have to assume that the statement holds for the ingredients that I needed to compose the last step. And then, OK. Now that we know what we need to prove, it's not so difficult. Now it is not so difficult. Anybody sees how to do that? Difficult step in many proofs by generalized induction is just to correctly phrase what is your induction hypothesis. Once we do it, the next step is easy. So, two questions. Anybody has a question about this? And the other question is how to do it. Or as my kids were saying, the way to ask, if you ask the class, does everybody understand? So nobody wants to raise his hand. But instead, if I ask the class, does anybody know the answer to does everybody understand? So the only person that can know the answer is someone who doesn't understand, right? Because if you understand, it doesn't give you an answer about whether does everybody understand. But if you don't understand, you know that it's not, the answer is no, not everybody understands. Right? So does anybody know the question to does anybody understand? Does everybody understand? Okay, yeah. So what did you want to say? Yeah.
Axiom 3.
Right, I'll use axiom 3. Right, I'll use axiom 3. Axiom 3 tells me that for all x beta equals gamma, arrows for all x beta, arrows for all x gamma. This is axiom 3. Now I can do modus ponens on this. And then I can do modus ponens on this. So I do modus ponens times 2. And I'm left with for all x gamma. OK, so we proved the generalization theorem. Are there any questions about this proof? Let us show that some uses of this generalization theorem, it sometimes make life easier. So here is an example of the use of this theorem. Assume I want to show that it is provable that for all x, for all y, r x, y, arrows for all y, for all x, r x, y. Again, intuitively, it is very clear. If it's just for all, then the order doesn't matter. But here we are in the domain of formal proofs. We want to show a formal proof. So we want to show a formal proof. So the first step will be to use the deduction theorem. So what does the deduction give me? Right, so the deduction by the deduction theorem it suffices to show that if I have as an assumption for all x, for all y, Rxy, I can prove for all y, for all x, Rxy. So let's do that. So I will start here, and I will prove this. How will I do it? I will write the following. I will write, here is my formal proof. I will write for all x, for all y, Rxy. Why am I allowed to write this? That's an assumption. Now I will write for all x, for all y, Rxy, errors for all y, Rxy. Why am I allowed to write this? Which axiom? Oh, axiom 4 adds a quantifier. This is exactly axiom 2. This is my alpha. This is my alpha. And this is alpha where x substitute x. Remember that? Do we still have it on the board or not? No, we no longer have it on the board. It's just that axiom 2, we said it's always the case that for all x alpha errors, alpha is always the case of axiom 2. And that's what we have here. So this is axiom 2. What do you mean? This is a formal thing. I call this alpha. Here I have for all x alpha. It errors alpha.
Oh.
I don't care what's inside alpha. So let me continue my formal proof. Now I will write for all y, Rxy, errors Rxy. Why am I allowed to write this? Same thing. This is axiom 2 again. So what did we get? We got that from this assumption, I can prove this statement. Right? So we got that from this gamma. This is my gamma. And it proves this alpha. So now I want to use the generalization theorem. What does the generalization theorem tell me? If I can prove alpha, and x is not free in gamma, then I can prove for all x alpha. Now, is x free here in my gamma? No. So I can invoke generalization. So we showed that for all x, for all y, Rxy, can prove Rxy. So now invoke the generalization.
Don't we still technically have to apply modus ponens twice to show that?
Yeah.
What?
We haven't quite shown that yet. We have to apply modus ponens first to have
Oh, there's a modus ponens. You're right.
And once
Few modus ponences?
To be able to apply that, we have to apply our
Oh, I didn't do the modus ponens here. I needed the modus ponens here to get for all y, rx, y. Yeah, I skipped them. And then add the modus ponens there to get rx, y. Okay, so you got yourself a bonus point. Yeah, definitely. I skipped 2 modus ponences. This is not excusable for you in the exam. Yeah. So I'm saying now I can invoke generalization theorem, because if I call this gamma and I prove this alpha, x is not free in gamma. Since x is not free in the assumptions, we get that for the same assumptions for all x, for all y, rx, y, I can prove for all x, rx, y. Because generalization tells me if I could prove alpha and x is not free here, I can also prove for all x alpha. Now, how do I do my last step? Right? Same thing. Same thing. Now invoke, since y is also not free in our assumptions, we can get now generalization again and get for all y, for all x, rx, y. Okay? So now in the exam I can ask you about for all y, for all x, for all z, and permute the order. So axiom 2 allowed us to strip the quantifiers, and generalization theorem allowed us to dress them again, put them on again, but then we can, now we can do like Superman and wear the underwear on top of our pants. So that's what we did here. We changed the order. Okay? So that's the generalization theorem. And now the next theorem that we want to show is the soundness, and I will not prove it because we are really running out of time in this course. There is the completeness theorem. So the next theorem is the completeness theorem. And the completeness theorem says that if gamma logically implies alpha, then gamma proves alpha. So if we go to our basic table of syntax versus semantics, we now have these symmetries. That here I can write gamma proves alpha, and here I can write gamma logically implies alpha, and this is the soundness, and this is the completeness. And if we continue with this table like we did with propositional logic, we can also get more kind of equivalences between statements. So here we had gamma is consistent And here we have gamma is satisfiable. And again, we can show implication in both directions. Now that we have soundness and completeness, we can show implications in both directions. So let us show it. Let us show those two implications following from here. So I have here a theorem. I did not prove the completeness, but we're assuming completeness. Assuming soundness, and completeness, gamma is consistent if and only if gamma is satisfiable. Okay, so how do we prove it? Proof. So the only main thing to note here, so assume we need to prove both directions. So look at this direction. If it's consistent, then it's satisfiable. So assume by way of contradiction that gamma is not satisfiable. I want to show you that it's not consistent. Now there is something to note. Note that in this case, note that in this case, gamma logically implies alpha for any alpha. Why is that? If it's not satisfiable, then it logically implies every alpha. Because what is the meaning of logical implications? Logical implication means every structure that satisfies all of the formulas in gamma should satisfy alpha. But there is no such structure. So this holds vacuously. Because there is no structure that satisfies gamma. Therefore, every structure that satisfies gamma dances tango or satisfies alpha or whatever you want to say. Because no such structures exist. Now, by completeness, we get gamma proves alpha for all alpha, violating the consistency of gamma. Because completeness tells me if it is logically implied, then it is provable. Okay, so now we need to go in the other direction. Are there any questions about this direction? So the other direction will be very similar. So this direction, assume gamma is satisfiable. And I need to show that it's consistent. right? So assume that it is satisfiable. So what I claim is for any gamma, for any alpha, or so satisfiable, so I know that peak M S such that M under S satisfies the formula gamma for every gamma in gamma. That's the meaning of satisfiability. I have some structure and I have some some assignment that makes all the formulas in gamma true. That's exactly our definition of satisfiability. So now, let alpha be any formula if M under S satisfies alpha, then by the definition of semantics, then by the definition of our semantics, M under S does not satisfy not alpha. Because we had an inductive definition of truth value. If you get true for alpha, you will get false for not alpha. We had an inductive definition of when is a formula satisfies in a structure. We started with atomic formulas, and then we showed how to extend it with quantifiers and connectives. And part of this definition said, if you satisfy alpha, now you want to check the truth value for not alpha, you'll use the truth table. And you'll get for not alpha, you'll get false. But now I have a structure that satisfies every formula in gamma, and it doesn't satisfy not alpha. So this demonstrates that gamma does not logically implies not alpha. Because I have my structure that satisfies every formula in gamma, and this structure does not satisfy not alpha. Now I invoke soundness. By soundness, therefore, gamma cannot prove not alpha. So here I cannot, if M satisfies alpha, gamma cannot prove not alpha. If M does not satisfy alpha, if M under S does not satisfy alpha, then by soundness, then we know that then gamma does not logically imply alpha, and then by soundness we get that gamma cannot prove alpha. So in any case, we got either alpha cannot prove not alpha, or gamma cannot prove alpha. In both cases, there is something that gamma cannot prove, and therefore gamma is consistent. So gamma is consistent. So we use soundness here, we use completeness there, And the end result is that by having soundness and completeness, we got that being consistent is the same as being satisfiable. Now, of course, we can talk about maximal satisfiable and maximally consistent and show that they are equivalent, but I can leave that to the exam. But in some sense, this proof is very similar to propositional logic. I didn't use anything which was specific to first-order logic. All I used is soundness and completeness and the definitions of consistency and the definition of satisfiability, which all have analogs in propositional logic. It's the same kind of proofs. Nothing here is special to first-order logic. Okay, so this is as far as I want to talk about pure logic. And now we come to the part of the course which connects it to computer science. It's about time. So we have 12 minutes now, and then we have all of next week. Okay, so I want to start with a fun notion that there are notions that in computer science that every computer scientist should know. But I want to start with a notion which is a kind of real fun and special, but not every computer scientist knows it. So you're going to be special. You're going to know something that not every computer scientist knows. And this is a notion which is called Kolmogorov complexity. So, yeah, it's complexity. Kolmogorov complexity. So I don't know if you have heard this name Kolmogorov before. It was a Russian mathematician of the previous century, and Alexei Kolmogorov, and he contributed a lot to the foundations of probability theory. But he also had this very beautiful idea which relates to computer science. Although he lived before computers were around. I mean, it's more in the style of Turing, you know. They had some real fundamental ideas about computing without having seen a computer. So Kolmogorov complexity says something like this. So usually when we talk about complexity in computer science, you assume that you have some task, and you ask how many resources do I need in order to carry out my task. I need to decide what is the shortest path for a traveling salesman, what is the minimum number of computation steps that I need to take to decide it. I need to decide if, I don't know what, if a formula has a bug. I want the compiler to find if there is a bug. How much time should the compiler chew on it until it can tell me whether there is a bug or not? But Kolmogorov was looking at it from, of course, as mathematicians. We don't have computers yet. We're not aware of how critical the time resource is. And he was thinking of the following. Assume that if I take any programming language can program every function. Every function that you can program in one language, you can program in any other language. You already know that, right? So let us fix a programming language. It doesn't matter which, because if you can compute something in one programming language, you can compute the same thing in any other programming language. So let us fix some programming language, your favorite, it doesn't matter. And now I want to talk about the complexity, not of a problem, but the complexity of a string. So we wish to define the complexity of a finite binary string. I could also talk about infinite strings, but I have a finite binary string. So I have a finite binary string, which is, say, 0, 1, 0, 1, 0, 1, 0, 1, and say the length of this string is 1,000, and I want to define the notion of the complexity of this string. And in some sense, we want to capture the fact that this string looks simpler than the string, I don't know what, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 0, something like that. Somehow this string is simpler than that string. So can you tell me in what intuitive sense is this string simpler than that string? Yes?
It can be compressed.
It can be compressed. It's one way of saying it. What did you want to say?
It's repeating.
It's repeating. So it's kind of the same thing. I can describe this string very simply. I can say, if I want to write a program that outputs this string, it's a very simple program. It just, for I goes from 1 to 50, write 0, 1, increase I to I plus 1. Right? So this is one way of writing it. I don't know in which language it was. So this guy has a short program that will output it. What will be the length of the program that will output it, such a string? Roughly, so if this is not 1,000, but if this is some n, what will be basically the length of the program in bits to output this string? Oh, much better than that. Yes.
Log base 2 of n.
Log base, right. Log base 2 of n. The program will be of length log of base 2 of n plus some constant. What will be the constant? The constant will you write for I equals 1 to n. N, to write n takes you log on base 2 bits. That's how many bits you need to write n. For I equals 1 to n, do print 0, 1, increase I to I plus 1. So this is a kind of a constant number of bits to write this program. And the only variable in my program is for how long should I run it. And I can write this number. It takes me log n bits to write this number. So this string, in some sense, has a short description because no matter what n is, I can describe the strings in log n bits, roughly. So let us go to the definition of Kolmogorov complexity. So Kolmogorov complexity of a string, it fixes a string, and say the Kolmogorov complexity of the string is the length of the shortest program in my language that will output this string. So the Kolmogorov complexity k of x is defined. This is our definition. It's the bit length of the shortest program. And remember that we fixed our programming language. So it is well defined. Otherwise, of course, you can now come up with a new programming language in which I could write it even shorter. But we fixed our programming language. It's the bit length of the shortest program that will output x and holds on the empty input. So my program doesn't take any input, or if I want an input, it will be part of the description, part of the program. So we know that for such a string, it is just log n plus a constant. So that's the Kolmogorov complexity of a string. And now we can say all kind of interesting things about the Kolmogorov complexity of a string. And it turns out that this is really, I mean, there's a whole book on Kolmogorov complexity which was co-authored by one of the professors in this department, which is, there's a book by Ming Li, how does he write Li? Yeah, maybe, I lie, yeah. And Paul Vitani. Which is called the Kolmogorov complexity. And it shows you, this book not only discusses, analyzes it, but also shows you all kind of applications to this. Like Ming Li has programs that do question answering based on Kolmogorov complexity. So, but we hopefully will get to seeing how some of the applications. But first of all, let's get a feeling of the Kolmogorov complexity of strings. So the problem is that I cannot describe to you strings that have long Kolmogorov complexity, right? If I want to tell you, here is a string of a long complexity, I cannot tell you, because to say here is, I have to describe the string to you, right? And I only have 3 minutes. I cannot describe to you a string of long complexity. So everything that we can describe is going to have a short complexity. So are there any strings which are have very long complexity? So here is a very small observation. For most of the strings, this is a very loose way of saying it, x, k of x is greater than the length of x minus 2. Okay, so I have to define exactly what I mean by most of the strings. But note that this is quite a surprising statement, because if I now want to describe to you as a typical string of length 2000, then I will have to talk now for 1998 bits, like just to describe to you this string. Because if I describe it in English, then I can write a program which will roughly be the same length as the English description. Because everything I say in English, you can kind of repeat in your program. So I cannot even describe to you a string of length 1000 that has complexity greater than 900, just because I don't have enough time. But on the other hand, what does it mean for most? If we just draw a string at random, so assume that I define the string as follows. I just flip a coin. Each time it falls head, I write 1. Each time it falls tail, I write 0. And I now flip the coin for 1,000 times. So what I'm saying is that with high probability, with probability 3/4, the string that I will generate cannot be described by a less than 998-bit program. So in other words, if we generate a string of some length n by repeatedly tossing a coin and unbiased 0, 1 coin, then for all large enough n with probability greater than a half, the output string, the string x that we generate will have k of x greater or equal than x minus 1 with probability greater than 3/4. I will have k of x greater than the length of x minus 2, and so on. Yes?
Can you describe the string by saying that this is the string generated by that guy tossing the coin?
It's not, doesn't it describe I mean, how, you have to tell me who is this guy and how did he toss a coin so that I will be able to reconstruct the string. Because I will try it with my coin and I'll get a different one. Okay, so we don't have to, you can think about it why this is true. It's not very it's just a counting argument. There are more strings than program to generate them. What? Oh, the minus 2 to get me 3/4. The minus 1 gets me a half. Minus 5 will get me 31/32. Okay, in general, you'll get x minus some number m. The probability will be, 2 to the m minus. Anyway, I don't want to. I don't want to eat your break.